Hello. Let's learn about polynomial theorems. This lesson is part 2 of our discussion of polynomials. So if you haven't watched the video about polynomial operations, you should do that first. Here are some polynomial theorems that you learned in Algebra 2 and Precalculus. The rational root theorem, the factor theorem, the remainder theorem, and the fundamental theorem of algebra. However, I am going to cross out the rational root theorem because I do not believe that that is explicitly tested on the SAT. For the other three, we will go over them briefly and I will remind you of how they work. Let's start with the factor theorem. Here's the statement of the factor theorem. If x equals r is a root of some polynomial, p of x, if and only if x minus r is a factor of p of x. Do you remember what this language if and only if means? Why don't you take a moment to discuss this as a class and see if anyone knows. Go ahead and pause the video. If and only if indicates the presence of a biconditional statement. Consider the conditional statement: if A is true, then B is true. And its converse: if B is true, then A is true. For many statements, the converse is not always true. For example, let's consider a statement: if an animal is a dog, then it is a quadruped. That statement doesn't necessarily work in the converse. If an animal is a quadruped, then it must be a dog? Well, no, it's easy to find counterexamples for that. However, if a statement and its converse are both true, you can write it as a biconditional statement and with a nice little double arrow, meaning it works both ways. And that's what we have here in the factor theorem. So if x equals r is a root of a polynomial, then x minus r is a factor. And vice versa. If x minus r is a factor, then x equals r is a root. Let's look at an example of this so we can employ our visual reasoning. Consider a nice little parabola. Let's say it has zeros x equals 2 and x equals 5. The factor theorem says if x equals 2 is a root, then x minus 2 is a factor. Similarly, if x equals 5 is a root, then x minus 5 is a factor. If you throw an a in the front, you can get an equation for your quadratic. You don't necessarily know what a is because there are multiple quadratics that have these zeros. Here are a few examples. There's no way to find a with this limited information. You would need some other piece of information. This also works in the other direction. That is, if x equals or x minus 2 is a factor, then you know x equals 2 would be a 0. That much should be obvious from the zero product property. Similarly, if x minus 5 is a factor, then x equals 5 is a 0. That's the essence of the factor theorem. We're going to see the factor theorem in action in a few examples a little bit later, but it's pretty simple. Let's go ahead and take a look at the remainder theorem, which is something you might be a little bit less familiar with. Here's a statement of the remainder theorem. It's very simple. The remainder of this polynomial division, p of x over x minus r, is p of r. Now you might recognize this particular setup for polynomial division as the setup that matches the use of synthetic division, and it is. And it's very common to be dividing by something that looks like x minus r. Why? Well, consider the factor theorem. We're interested in whether or not x minus r is a factor. So let's get a sense of what the remainder theorem says by actually trying it. The remainder of this division should be p of r. So here's a division problem for you. Go ahead and take a moment and try to divide. For fun, I'd like you to try and divide this using long division and also using synthetic division. Do it both ways and check and make sure you get the same answer. Go ahead and pause the video and try doing this division, and then we will discuss how the remainder theorem applies to it. Okay, I'm going to do the long division first. So I'll do that in brown. X plus 2 goes into 3x squared plus 7x minus 2. And I'm going to go through this quite quickly, so be sure to ask questions if you have any. I started off by making a mistake. But because I'm writing things out, I'm able to catch my mistake and hopefully not make any more. So the answer is 3x plus 1 with a remainder of negative 4. In this case, we're interested in negative 4. I'll go ahead and write out the answer just so you can see it. 3x plus 1 with a remainder of negative 4, which is still over x plus 2. That would be the result of the division. I'm going to try the same thing using synthetic division, which is easier. Remember, there's a negative 2 here because it's dividing by x minus negative 2. Every time you get to the bottom, multiply by r. And that's a remainder. So this means 3x plus 1 with a remainder of 4x plus 2. And it, of course, does match. If you have any questions about what I did here, now would be a good time to pause and ask them. Let's look at the remainder theorem and how it applies to this problem. The remainder theorem says the remainder of p of x over x minus r is p of r. We were dividing by p of x over x minus negative 2. So this would be x minus negative 2. So the remainder theorem says p of r, that is p of negative 2, is equal to the remainder. P of negative 2 is negative 4. And you could get this from either method. Why would you want to know this? Well, I don't really have time to go into why this is so useful, but let's just say for now that if you've done the division, this is an easy thing to know. P of negative 2 is negative 4. Notice you could have evaluated p of negative 2 simply by plugging in negative 2 for x. This is our p in this case, so let's try and calculate p of negative 2 and check and make sure that it does indeed give us negative 4. Take a moment, pause the video, plug in negative 2 for x, and evaluate p of negative 2. So we get 3 times negative 2 squared, which is 12 minus 14 minus 2, which is negative 4, and so it works. Okay, out of context, this doesn't seem like the most useful thing ever, but oh well. Now you know the remainder theorem. Let's take a look at another example problem, this time from the SAT. This was actually from the first test that we took, and I want to give you a little bit of time to think about it and consider use of the factor theorem and the remainder theorem. Go ahead and pause the video and give this a think. Okay. P of 3 is negative 2. If we apply the remainder theorem to this, then the remainder theorem says the remainder of p of x divided by x minus r, in this case 3, is equal, the remainder of this is negative 2. And that's exactly what answer choice D says. So answer choice D is exactly a statement of the remainder theorem from what I've circled here in blue. The others may be true, may not. Who knows? We have no information about whether or not these are true. These are total airballs. They're totally off base. Which of the following must be true? This is exactly the remainder theorem. So that's why I was teaching the remainder theorem. If you see this remainder, go question, you have two options. You can either calculate the remainder by doing the division, or you can use the remainder theorem. Well, in this problem, you cannot do the division because we do not know what the polynomial p of x is. So, pretty specific piece of knowledge. I don't know exactly why they decided to keep this on the SAT, but there it is. Go ahead and ask any questions about this if you have them. Next, we have the fundamental theorem of algebra. The fundamental theorem of algebra essentially says, well, this isn't exactly it, but this is a consequence of it. Every polynomial of degree n has exactly n roots. That's why when you're solving a quadratic, you know you have 3 roots. I'm sorry, 2, because a quadratic is a polynomial of degree 2. However, this does not mean that they're always real roots. When we talked about quadratics, we talked about 3 options. A quadratic that has 2 distinct real roots, or a quadratic that has a repeated root. This might be something like x minus 2 squared, which has a repeated root at x equals 2. Does this violate the fundamental theorem of algebra? No. It still has 2 roots. Imagine solving with a zero product property. You would still get x equals 2 or x equals 2. It's just that they're both the same. This does not tell you that they will be distinct. So you could have 2 distinct real roots or 2 roots that are repeated. Do you remember the other option? The other option was if this has 2 complex roots. So this still has 2, but they could be complex. So this does not guarantee the presence of real roots. Consider, Consider a polynomial of degree 3. There could be 3 roots. Or you could have 1 real root and then 2 more real roots that are repeated. So let's say this was at -1 and this is at 2. Using the factor theorem, we could make factors out of these. If x equals -1 is a 0, then x minus -1 or x plus 1 is a factor. And similarly, if x equals 2 is a root, then x minus 2 would be a factor, and we have 2 of those, and you can get a polynomial of degree 3. If you're suspicious about this, you could graph it on Desmos and check and see that it looks like this, and it does. You could also have a polynomial of degree 3 like this. What's the situation here? Well, there's 1 real and 2 complex for a total of 3. So cubic is a polynomial of degree 3, and in any way you look at it, it has 3 roots. That's the fundamental theorem of algebra. Now, you can use that information to help you solve polynomial equations. Consider this one. This is a real fun one. Consider this function. Now, when I interview potential tutors to work in PLC, I ask them this interview question. I ask them to solve this problem, solve this equation. And I'll show you what most of them do. First of all, they add 1, and then do a cube root of both sides. Oops. And they get x equals 1. Ta-da! What do you think about this? Do you think this is right? Take a moment and pause the video and discuss this. Well, hopefully, someone was able to recognize that something's missing here, because this is a polynomial of degree 3, and according to the fundamental theorem of algebra, there should be 3 zeros. So where are they? This is only one of them. But maybe this is a triple repeated root. Maybe there are 3 zeros, but they're all equal to x equals 1. That's not true. You can tell that that's not true because you can graph this. This looks like an x cubed function with a -1 moving it down 1. So you can tell that it does a whoopty. It's not a triple repeated root. This is an ordinary root. A triple repeated root for a cubic polynomial would look something like in y equals x minus 1 cubed, which is a regular cubic moved right one. Oops, let me try that again. And it has this kind of zigzag wiggle thing. It looks like it's going to do a repeated 0 of multiplicity 2 and turn around, but then it changes its mind and it goes through anyway. This is what a triple repeated root looks like, and you can see that's not what we have. So we have one root, and we know that there are two more, because there have to be 3. This is x equals 1. So where are the other two? That's right, they are complex. How can we go about finding them? Why don't you discuss for a moment as a class and see if anyone has a good idea for how you can find the other solutions. Okay, I'm hoping that someone was able to come up with the factor theorem. We know that x equals 1 is a root. Therefore, you know x minus 1 is a factor. Okay, so consider x cubed minus 1. We can go about factoring it. Whoa, a little squirrely. So we have x cubed minus 1, which we know we can factor into x minus 1 and some other stuff. How do we know what this other stuff is? Well, the secret is to divide. Divide both sides by x minus 1 so that you can cancel these and you can solve for this other factor. And guess what? We just reviewed how to do division. Would you do long division or synthetic division here? Either one should work. This does fit the form of synthetic division. Pause the video and do the division and calculate this unknown factor. Okay, I'm going to do the synthetic division. Now when you do synthetic division, remember how you're using columns, like placeholder columns instead of writing the x's. So you have to write 1x cubed, 0x squared, 0 x's, and minus 1. If you don't include the zeros, then you're going to get it wrong. So in synthetic division, the columns are important, so you need placeholder zeros for x cubed minus 1. Okay, so I'm going to put my box, and off to the side I'm going to put 1. Remember, we're testing x equals 1. Bring down the first 1. Every time you get to the bottom, multiply. So 1 times 1 is a 1. Add. Multiply. Add. Multiply. Add. And you get 0. That's the remainder, and the remainder is 0. Is it a surprise that the remainder is 0? No, because we already knew that x equals 1 was a root. Therefore, we knew x minus 1 was a factor. Therefore, we knew that it would divide with no remainder. That's what it means to be a factor. So this means x squared plus x plus 1. So we have found our other factor. We have found that x cubed minus 1 can be factored into x minus 1 times x squared plus x plus 1. Great. Now if we want to set this equal to 0, we can use the zero product property. Either x minus 1 equals 0, which gives us the solution, of course, we already had, or x squared plus x plus 1 equals 0, which is a quadratic, and we can solve this quadratic by completing the square or the quadratic formula. You're not going to be able to factor this, I don't think. Pause the video and solve this quadratic. I'm going to solve by completing the square. So first of all, I will subtract 1 from both sides to make room. And my perfect square is going to be x plus 1/2, so I need to add 1/4 to both sides, giving me minus 3 over 4. Do the square root, and when you do the square root, don't forget plus or minus. And we also have the square root of a negative, which is going to be root 3 I over 2. I went ahead and did the square root of 4, which is 2, and solve for x by subtracting. And you get this as 2 solutions. So now we know all 3 solutions. We know x equals 1, and we have these 2 here. And it's a polynomial of degree 3, so it has 3 roots. And we found all of them. So like I said, I give this problem to potential tutors to see if they know what they're talking about and to see how they would analyze this problem. And the first clue is that it's a polynomial of degree 3, so it must have 3 solutions. If you have any questions about what we did here, go ahead and pause and ask them. Okay. Here's a sample problem. This is from Khan Academy. So go ahead and pause the video and give this problem a try. All right. Hopefully you were able to factor this. The first step of factoring, don't forget, is to factor out a common monomial. In this case, 2x. Then you have the difference of 2 squares, which is x minus 3 and x plus 3. So the zeros are x equals 0, x equals 3, and x equals negative 3. There are 3 zeros because it's a polynomial of degree 3. Oop. Now, if for whatever reason you couldn't factor this, and you just were messing up the algebra, you could still get this problem right. How could you cheese this problem even if you had no idea how algebra works? That's right, you could plug in numbers. The answers are here, all you have to do is test them. You could test a and b by trying 2, or negative 9, but I would try 2, just by plugging it in to see if you get a 0. And you wouldn't, and so you could eliminate a and b. You could differentiate between c and d by testing x equals 0, and x equals 0 obviously works. So the answer choice must be D. But this is easy to factor as well.